Okay, in this second video for chapter 2, I want to try and explain problems involving or motion involving constant acceleration. Let's start by thinking about graphs. If I graph acceleration versus time, I get a graph that looks like this. That's a constant acceleration. One of the types of constant acceleration we're going to talk about in a few minutes is free fall. Anything that falls near the surface of the Earth falls with an acceleration of 9.8 meters per second squared. It's constant. What would velocity look like with constant acceleration? This is time again. Well, if I think about it, I'm going to start with some initial velocity. I'm going to call that v0. But if I have a constant acceleration, remember acceleration is the slope of a velocity time graph, which means I have a constant slope. So that would look like a graph that would just be straight. Now, I drew it with a positive constant velocity. It could have a negative constant velocity, but I drew a positive constant velocity here. So I drew a positive constant velocity. I can write an equation for that. That would be v equals the velocity at any given time, v0 plus the acceleration times the time. How did I know how to write that so easily? Y equals mx plus b. But in this case, the y-intercept is v0, the slope is acceleration, and the horizontal axis isn't an x, it's time. Acceleration times time plus the initial velocity equals v. It's not y, it's v. This is just y equal mx plus b. That's one of our really, really important equations. Super important. Our second really, really important equation relates to displacement. If you have a constantly increasing velocity, your position graph is going to start off with some initial position, but it's not going to increase at a constant rate because the velocity isn't constant. The velocity is increasing. So you'll get a situation where you'll be increasing at a faster and faster rate. In fact, what you get is a graph of a quadratic. We went from a constant function to a linear function to a quadratic function. When you get my notes, I derived this next equation for you very carefully in my notes. It's also derived in the textbook, but I'm not going to derive it right now. We get another really important equation that says your position is equal to your initial position, x0. All this little subscript, some people read it with a naught, v naught. It means your initial, v0, v naught, x naught, or x0, plus v0t, v naught t, plus 1/2 a t squared. Now, the important thing to remember is that those two equations are great equations. I can solve lots of problems with them. But they only work if we have a constant acceleration. They won't work if you have an acceleration that varies with time. There are some other equations. For one thing, we can create an equation if we solve this for t. We get something like t equals v minus v0 over a. If I solve that and I tuck it in here for t here and t here, and I have that written out on my paper, and I spend a lot of time doing algebra, and I don't want to do that on this video, cleaning up that algebra, I can get another equation that doesn't depend on time. I'm going to start writing these equations in a list. They're really important equations. So, constant acceleration equations. The velocity at some time is v0 plus at. The position is x naught plus v naught t plus 1/2 at squared. If I solve this top equation for t, remember I said that would be t would equal v minus v naught divided by a, and I plug that in there both places, I can come up with another equation that looks like this. But usually that's not the way we see it. Usually we rearrange that. First of all, that's delta x. And I get v squared minus v naught squared is 2a delta x. That's a relationship that relates your displacement to your initial and final velocities without actually requiring time. Probably don't want all this in here cluttering it up. So we've got 3 equations so far. There are sometimes some others given, but I feel like those are actually probably what, here is the one more I was looking for. For constant acceleration, only for constant acceleration, your average velocity is just v0 plus v divided by 2. Now think about that. This is almost common sense. If you have a constant velocity and you start off going 0 meters per second and you end up going 100 meters per second, picture it on a graph. Here's time, here's velocity. If I start off going 0 meters and I end up going 100 with a constant acceleration, my average is right in the middle. My average, if this is 100 meters per second, that will be 50. That was 0. So if you have constant acceleration and you know your beginning velocity and your final velocity, you can find the average. You just average them like you average any 2 numbers. But that gives us another interesting equation. It tells us that our displacement will equal v0 plus v divided by 2 times the time. Your displacement is just your average velocity times your time. Makes sense. If your average velocity is 25 miles an hour, in 1 hour you'll go 25 miles. In 4 hours you'll go 100 miles if you're going 25 miles per hour. So we've got 4 really nice equations. One for determining velocity, if we know the acceleration and time. One for determining position. One that relates those two that we've gotten taken time out of the picture. And then finally one for using average velocity to find displacement. If you said which one's most important, I'd say those two are a tie. But these are sometimes just handy. I solve most problems with these two, but I also use those from time to time, particularly this one. All right, so the rest of this, I really want us to just get really good at solving problems. I'm going to have to erase these, so hopefully you've got your formula chart printed out or you've written these down. You can stop the video and write them down now. We're going to primarily solve problems that involve constant acceleration. Those are going to be the main problems we solve. Notice I threw in a vocabulary word, kinematics. Kinematics is the study of motion, which is what we're doing now. It's just a fancy physics word that says we're studying motion. Hence, you've heard KIN for other things involving motion, kinetic energy, kinesiology. It's where it comes from. First thing you want to do, I want you to read that problem. Probably twice. Why are you going to read it twice? Well, the first time you read it, you get a feel for it. And the second time you read it a little more carefully now that you know what's going on. Read that problem. If it's helpful, and it often might be, draw a picture. Sometimes the problem's really easy and you really don't need a picture because you're thinking, I know exactly what that looks like. He said I'm stopped at the stop sign and I accelerate with this speed for this many seconds. I don't need a picture. But sometimes the picture helps a lot. That's going to be even more true when we start solving not kinematics, but dynamics, things with forces. Pictures are going to be lifesavers when we get to forces. Read that problem, draw a picture. That second time you read through, or the third time, you want to identify everything you know. Do I know the initial velocity? Do I know the displacement? Do I know the acceleration? Do I know how much time elapsed? Write down every quantity that you know. It's hard to find the right answer if you don't know what you're looking for. Did they ask me to find the time? Did they ask me to find the displacement? How far? That's probably a distance or a displacement. How long? That's probably a quantity of time. How fast? That's going to be a speed or velocity. What am I trying to find? Once you know what quantities you know and what quantities you're looking for, find an equation that relates what you're looking for, the unknown and known quantities. I gotta find the equation that will take what I know and I can use it to find what I'm looking for. Once you do that, substitute and solve. Plug in all of those known quantities into that equation and solve for that unknown quantity. Finally, here's the one people don't want to do. Check for reasonableness. Does the answer make sense? Sometimes I know in physics the numbers are so large or so small you're not sure if they make sense. But in that case, at least you can check kind of order of magnitude and make sure that the math makes sense. But in other problems, you should have a pretty realistic feel for things. You'll get a better gauge of how fast things should be moving or what. But just look at the answer and make sure that when you're done, you think that that was a reasonable answer to get. All right, let's work a problem. I'm going to read the problem. If you print off my notes, you'll have a copy of it, so I don't want to waste a lot of time writing it all down. But I'm going to write down the key things the second time I read through. It says a car initially traveling at 15 meters per second. And we're going to assume these are straight line problems. We haven't learned to turn corners yet, so this is a linear problem. The car initially traveling at 15 meters per second accelerates constantly at 2 meters per second squared in order to pass a truck. What is the velocity of the car after 5 seconds? The car initially traveling at 15 meters per second. They just told me V0 is 15 meters per second. Accelerates constantly. Well, that's important because it means my constant acceleration formulas are going to be useful. At 2.0 meters per second squared. Another thing that helps you realize what they're telling you is units. Meters per second squared has to be an acceleration. Meters per second has to be a speed or a velocity. So it accelerates constantly at 2 meters per second in order to pass a truck. What is the velocity of the car after 5 seconds? Well, they're telling me the time is 5 seconds, and they're asking me what V is. It's pretty easy. I want to find V. I know V0, I know A, I know T. That looks exactly like this formula. So I know what formula to choose. That's going to be 15. If you accelerate at 2 meters per second squared for 5 seconds, you will gain 10 meters per second. That seemed almost too easy. Here's a part B. The question says, how much more time until it reaches 35 meters per second? So we're going to change the question. The question is if V equals 35 meters per second, how much time did that take? It's the same formula. It's the same acceleration. But we've got a different time, and so I don't need that anymore. Okay. If I use V equals V0 plus AT, and this time I'm trying to solve for time. This is 35 equals 15 plus 2 times T. Takes us back to Algebra 1. I got to subtract 15 from both sides. So 20 equals 2T. T equals 10 seconds. Now, that really didn't answer the question they asked. They said how much additional time. So if it takes 10 seconds to reach 35, the answer is it's going to take another 5 seconds. It took 5 seconds to reach 25 meters per second. It takes another 5 seconds to reach 35 meters per second. Oh, let's leave our information up here. Same car, initial velocity is 15 meters per second. Acceleration is 2 meters per second squared. Only now the question says, how far does the car travel during the first 5 seconds of acceleration? How far does the car travel? We can think of that as saying, what's really the displacement here for linear motion? Or there's a couple of approaches. A lot of the time, I just say, hey, let x0 equal 0. We might as well let that be the beginning point. And now I just need to find out how far it went. That's probably the best approach. My equation looks like this. I'm going to let it start off at 0. One of the nice things is I can pick my own frame of reference. And when I do, I probably want the problem to begin at 0. T equals 0, x equals 0. So what will be my position? This was 15. This is 5. Notice I'm going to show you something. If you don't have any acceleration, if the acceleration is 0, this goes away. And really what you find out is how far you travel is just your speed times your time. If we don't accelerate, he'll just go 15 meters per second for 5 seconds or 75 meters. But we are accelerating, so it's going to be more than 75. Plus 1/2 times 2 times 5 squared. That's going to be 75. Half of 2 is 1 times 25, that's going to be 25. So the car will travel 100 meters. There is another way if we wanted to. Do I want to? I could use the fact that we came up with this earlier, that your displacement is really just equal to your average velocity times your time. Well, remember, we figured out a few minutes ago that when he accelerated at the end of that, his final velocity was 25. His initial velocity was 15. The time was 5. Well, the average 25 plus 15 is 40. His average speed was 20 meters per second for 5 seconds. So he traveled 100 meters. About the only reason to show you this other way is to remind you that when you do it right, you get the right answer. And in physics, a lot of times there really is more than one approach to solve the problem. But if it's valid, you're going to get the same answer, even if you and I choose a slightly different one. Let's do another. to read it again. You can look at it in your notes. A car at rest accelerates at a constant 4.9 meters per second squared. What distance does it travel in reaching a speed of 30 meters per second? So a car at rest. A car at rest has a velocity of 0. A lot of times, initial or final velocities are camouflaged into problems by saying the car came to a stop. Well, that means the final velocity was 0. It began at rest. Look for those words. So a car at rest, V0 equals 0. Accelerates at a constant 4.9 meters per second squared. The constant tells me that I'm using these constant motion formulas. What distance does it travel in reaching a speed of 30 meters per second? Well, this 30 meters per second is our final speed. And it wants to know our final position. I like to let the initial position be 0. How far does it travel? If it started at 0, where is it now? Notice they did not tell me the time. They don't tell me the time. I have two choices. I can solve for the time very easily using those other two equations, or I could use this formula. Let's use this formula, and then we'll do it the two-step one. I have a formula that says v squared equals v0 squared plus 2a delta x. V squared equals v0 squared plus 2a delta x. This is 30. This is 0. This is 4.9. And I can just find the displacement. So 900 equals 9.8 times the displacement. Comes out to be 92 meters. That's the one-step way, by using that third equation where they already got rid of time since we didn't know time. But another approach that I might use is this one. V equals V0 plus AT. I know this was 30. No, this was 0. This is 4.9 times t. If I solve that, I can find out that the time to do this is 6.12 seconds. Now, I was not asked to find the time, but now that I know the time, I can use this. I let that be 0. Let that be 0. Plus 1/2 times 4.9 times 6.12 squared. Notice all of that's 0, so I just have to end up multiplying what is 1/2 times 4.9 times 6.12 squared. Well, to two significant digits, it comes out exactly the same. The problem had two significant digits given at the beginning, so that's why I rounded my answer to 2 at the end in both cases. Now, I have some more examples, but I'm going to save these more examples for when I meet with you face-to-face or virtually. Let's move on and let's talk about free fall. For a long time, and when I say long time, I mean all the way back to Aristotle. So we're talking BC. I'm not sure how many, roughly 50 to 100 years BC, I think. Could be off on that. Everybody knew heavy things fell faster than light things. It was generally accepted. Things fall at different rates. Obviously, feathers don't fall at the same speed as a rock. That's true if air resistance is a factor. If I drop a sheet of paper and I drop this marker, they're going to hit the ground. Let me try this on this table. Let's see if I can make it happen. I'm going to need a blank sheet of paper that I can wad up. I don't want to wad up my notes. But if I drop them, and I have a table right here, hopefully you can see it. Clearly the marker hit. You heard it clearly. But if I take this sheet of paper and I crumple it up, so it's more like a rock and less air resistant, they'll probably hit at the same time. I don't know if you saw that. I'll do it again. You can slow it down, but I think they did. Pretty close. It was Galileo who figured out, hey, you know what? In a vacuum, everything would fall at the same rate. It wouldn't matter which objects were more massive. And you can even see videos in a vacuum where things like pennies and feathers all fall at the same rate. If you Google a hammer and a feather on the moon, which has very little air resistance, you can see where one of our astronauts dropped a feather and a hammer on the moon's surface. And they hit, the moon, above the moon's surface, they hit the ground at the same time. So we owe this to Galileo. Acceleration is constant. It doesn't depend on the object size or weight or mass if, and this is a big if we can ignore air resistance. Sometimes it's appropriate. If we're dropping cannonballs, it makes sense to ignore air resistance. If we're opening a parachute, we can't ignore air resistance. Parachutes are all about the air resistance. Okay. As long as we're near the Earth's surface, everything has an acceleration due to gravity. And that acceleration is represented with a lowercase g. It's 9.80 meters per second squared. Now, occasionally you'll find a book that uses a slightly different value, but not too often. That's the SI unit. You can write it as 980 centimeters per second squared. If we were working in centimeters, that would be true. If we're working in feet, we can say that it's 32.2 feet per second squared. Both of these come up once in a while, but this is what we use almost all the time. If we're not near the surface of the Earth, what if we go someplace else? They will also have a constant acceleration near their surface. If we go to the moon, G has a value of about 1.62 meters per second squared. It's about 1/6 the acceleration due to gravity here on Earth. We often say that the moon has 1/6 the gravity. If we go to the sun, which would be a little trickier, we would find that G was about 274 meters per second squared. Now, acceleration is a vector. Most of the time when we are doing problems that involve falling objects, whether they're actually falling or whether we're throwing them straight up, we're going to let down be negative and up be positive. Now, the value of G is generally stated as a positive. But if we have something falling in our problem, our acceleration will probably be negative 9.80 meters per second squared. And the only difference is the negative is indicating direction. Okay, so when we're thinking about using it in a problem, we need to really be careful. Some free fall problems, when everything's falling, we do define downward as positive. If we do that, that's great. We just then everything, acceleration will be positive, velocity, displacement. However, if we define it where up is positive and down is negative, then the acceleration would be negative. So this is a positive quantity that represents the magnitude of the acceleration due to gravity. You have to look at your problem and decide how you're setting up your frame of reference as far as how are you going to use it. All right. Let's do an example. A coin is dropped from the leaning tower of Pisa. I don't think we know this to be true factually, but legend has it that Galileo dropped cannonballs off the leaning tower of Pisa and timed their fall, and that's how he determined that it didn't depend on mass. We're asked to find two things. Find position and time at t equal 1, 2, and 3 seconds. And we'll try to keep everything to 3 significant digits. Since I gave us the time in 3 significant digits, we know the acceleration. We'll go ahead and we'll let down be negative like we do most of the time. We know that our position is given by that formula. However, let's stop and think about, we know if we drop something, V naught is 0. If we consider the top of the tower to be 0, this might be a case where it's good to draw a picture. Here's the leaning tower of Pisa. There's a little lean. And here's the coin. It's going to fall like this. We're going to let this be. Oh, and I want to change this. This is the one thing I meant to do. Usually if I'm going to work a problem that's vertical, I'm not going to use x's. I'm going to use y's. So I'm going to say that up at the top, y is equal to 0. I can do that. I know that V naught, also 0, because we dropped it. What else do I know? I know I have a constant acceleration that points down. That's everything I know. This formula is going to give me my position. This formula is going to give me my velocity. Notice by filling, let's do the velocity one first. This is going to be 0. This is negative 9.80. The acceleration is negative, it's falling down, times t. So if I make a table, here's t, here's v, here's y. At t equals 0, my velocity was 0, my position was 0. Remember, it's my frame of reference. If I want to let the top of the tower be 0, that's fine. At t equal 1 second, negative 9.80 times 1 second, I'm going to be falling at negative 9.80 meters per second. That makes perfect sense. My acceleration is 9.80 meters per second every second. So every second I fall, I'm going to pick up 9.80 meters per second. If I wait 2 seconds, this is going to be negative 19.6 meters per second. 9.80 is almost 10. If you want to mentally estimate, you can think it should be about negative 10, negative 20, negative 30. Not quite, but close. If I wait 3 seconds, I get negative 27.4 meters per second. So velocity is really pretty easy. Just negative 9.8 times the time. Position's gonna be easy too. First of all, look at the formula right here. Well, when I look at that formula, one of the things I notice is y0 is 0, so that goes away. v0 is 0, so that goes away. And I'm really left with that my position y is equal to 1/2 negative 9.80 t squared, or negative 4.9 t squared. That means when t is 1, negative 4.9 times 1 squared, I will have fallen 4.90 meters. A lot of people make the wrong mental jump. They say, oh, you're accelerating down at negative 9.80, so in 1 second, you'll fall negative 9.8 meters. No, 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 no. You started at 0. Your average speed from 0 to 1 second is actually half of this, negative 4.9. If we plug in 2 squared, 4 times negative 4.9, much on coincidence, we get negative 19.6 meters. If we plug in 3 squared, we get negative 44.1 meters. Pretty easy. We just needed those same formulas and that constant acceleration. Let's keep the problem, but let's erase the table. I do want you to remember, after 3 seconds, it's fallen about 44 meters. Just keep that in your mind. Keep the picture. If the tower is 47.0 meters tall, when does the coin hit the ground? Well, if it's 47 meters tall, then when it hits the ground, y will equal negative 47.0 meters. Now, I could have started with positive 47 here and this is 0. It actually comes out the same either way. If this is positive 47 and this is 0, from here to here is a loss of 47 meters. If this is 0 and this is negative 47, here to here is a loss of negative 47 meters. It's the same thing. Okay. Remember a minute ago? Y equals y0 plus v0t plus 1/2 at squared. But we said that's 0, that's 0. This goes away. This goes away. Y is just 1/2 negative 9.8 times t squared, or negative 4.9 t squared. When I'm trying to solve for t, I know how far it will fall. It's going to fall negative 47.0, negative 4.9 t squared. Remember, at 3 seconds, it had fallen 44 meters. So my intuition says this is just going to be a tiny bit longer than 3 seconds. So negative 47 divided by negative 4.9. Take the square root. Whoops, I don't know what I did, but I didn't take the square root. Take the square root. And t is 3. Comes out 3.097, but I only have 3 significant digits, so 3.10 seconds. We said it'd be just a little over 3 seconds, and it came out just a little over 3 seconds. I could ask how fast it was going when it hit the ground. And when I say how fast is it going when it hit the ground, I don't mean 0. I know once it strikes the ground, it will stop moving because I mean, how fast was it going when it struck the ground, before it stopped? So we're talking about the smallest fraction of a second you can think of before it hits the ground. To find that out, I need to know the time. V equals V0 plus AT. It started off going 0, negative 9.80. If it falls for 3.097 seconds, notice I don't really want to round early ever. 9.80 times that answer, so times 9.80. And I find that it's going to be going about 30.4 meters per second. It's going to be negative because the negative indicates that it's falling downward. That's what that negative indicates. We're not surprised then that it has a negative velocity. It had a negative acceleration. All right, let's do another problem. Only this time, let's kind of change it up a little. Let's throw something upward. Now that might not sound like free fall. We think of free fall in our minds as being dropping something. But if I throw it straight upward, it just means it's going to have initial velocity that's positive. But the only force it's acting on it is still gravity. So in a sense, it will still be freely falling. It just didn't start from rest with a velocity of 0. It's going to start with a positive velocity. If you throw something up and it comes back down, let's suppose I throw something up. And let's use the acceleration due to gravity as being negative 10. It's easier than negative 9.80 if we just want to rough out a problem. Suppose I throw it up at 30 meters per second. It has a positive velocity of 30 meters per second, but it's got this negative acceleration of 9.80 or negative 10. We know it slows down because if it has a positive velocity and a negative acceleration, speed slows down. So what does that mean? If it's slowing down at 10 meters per second each second, if I throw it at 30, 1 second later it'll be going 20. 2 seconds later it'll be going 10. 3 seconds later it's going to be going 0. If it's going 0, that means it's momentarily at rest. But remember, the acceleration never changes. 1 second later, it's going negative 10, then negative 20, then negative 30. In fact, the trip up and the trip down look exactly alike. We have this symmetry. Draw a picture. At least going 30 meters per second. And it goes straight up. It goes all the way to the top. At the top, V equal 0. At the top of a motion, when you throw something up, the vertical velocity will be 0. And then it's going to come back down. When it hits down, it's actually going to be going negative 30 meters per second. But the trip up and the trip down take the same amount of time if you launch and land at the same height. All right, let's do a problem. Let's do an interesting problem. Interesting is code for something that's maybe just a little bit harder. let's have somebody standing on top of this building. He's going to throw up something, this ball. There's my little stick person. It leaves his hand going up at 15 meters per second. But he holds his hand out over the edge of the building, so it's actually going to come right back down. It's going to reach its maximum height, and then it's going to fall back down. It just clears the building. Okay. You threw it up with an initial velocity of 15 meters per second. You've got an acceleration negative 9.80 meters per second squared. They asked me to find the velocity at 1 and 4 seconds. So we're going to find two different velocities. How fast is it going at 1 second? How fast is it going at 4 seconds? So there's our basic velocity formula. This was positive 15 minus 9.80 for 1 second. And we see it's going to be going 5.20 meters per second. If I find out how fast it's going at 4 seconds, I'm going to need a calculator this time. 15 minus 9.8 times 4. I'm going to be going a negative 24.2 meters per second. What that tells me is the ball is on its way down here. It was still on its way up after 1 second. It's on its way down at 4 seconds. If I want to find out when it reaches its maximum height, what happens at the maximum height? Really need to remember, the maximum height, the velocity is 0. It's no longer going up, and it's not coming down. It's that transition from going from a positive to a negative. Well, the only way to go from a positive velocity to a negative velocity is to have a velocity of 0, just instantaneously. So if I say v equals v0 plus at, I want to know when is that velocity 0. This was 15. I can see that it's going to be 15 divided by 9.80, 1.53 seconds. That's the time where it reaches the maximum height, or where the velocity is 0. If I know how long it takes to reach the maximum height, it's not hard to figure out what that maximum height it was above where it's thrown. I don't know how tall the building is. I could fill in a height for the building, but I think I'm just going to figure it out just how much higher than this it is for now. And then I may tell you how tall the building is. We just figured this out, so we'll keep that piece of information. It had reached its maximum height at t equal 1.53 seconds. If we use our vertical position formula, we're going to call this 0 for now. We're going to just see how far above if I let y0 equal 0, we're just going to go from here to here. Watch the sign. Make sure you put in that negative acceleration. Okay. 15 times 1.53 minus 4.9 times 1.53 squared. Get 11.5 meters. We can do some interesting things now. Let's ask a question. If it hits the ground in, let me write this up, right there. Suppose it hits the ground and we'll just make an easy number in exactly 6.00 seconds. Let's ask some questions. First of all, can we figure out how far it traveled? Can we figure out how tall the building is? I think we can. We don't know how tall the building is, but we'd really, really like to know. If I want to do that, I probably could just look at the second half of the problem. Do I want to look at the second or want to look at the whole problem? Let's just look at the whole problem. Y equals y0 plus v0t plus 1/2 at squared. If I want to know how high it was when it was launched, let's suppose I want to know this height. I want to know how tall this ball was thrown above ground. Let's suppose you held it, he might have even held it down where it was exactly the height of the cliff. This is going to be y equals 0. I'm going to set it up where the ground is 0, and this is some unknown height. That seems reasonable. The ground is 0. This is some unknown height. That's what I'd like to know. The initial velocity was positive 15. It was in the ground, it was in the air for 6 seconds, so I know my time. Negative 9.8 times 6 squared. I just made this problem up, so let's see what I came up with. 15 times 6 is 90. I left out my y0. y0 plus 90 minus 176.4, and I can quickly find out that y0 equals 176.4 minus 90, 86.4 meters. That's the height of the cliff. That's how high it was where it was launched at t equals 0. I can answer other questions. I can say, well, what is the distance the ball traveled? Well, let's think about it. It went up 11.5 meters. That was the maximum height. It came down 11.5 meters. But remember, if I'm doing distance, everything is positive. And then it went down another 86.4. 11.5 plus 11.5 plus 86.4. It traveled a distance of 109.4 meters. This was the way up. These two combined was the way down. We already figured from here to here was 11.5 meters, so it came down another 11.5 meters. Plus, we figured out that the height here, this initial height, had to be 86.4 meters. Same equations we were using a few minutes ago when we were going horizontally with cars accelerating. Now they're just vertical. And now we have a constant acceleration of 9.8, negative 9.8. I think any more problems I'll save until we're together in person. I do want to talk just very, very briefly about relative velocity. In order to describe something's motion, you have to have a frame of reference. Most of the time, the Earth is our frame of reference. We tend to think the Earth is completely stationary on a day-to-day basis, but we actually know the Earth is rotating, it's orbiting the sun, we're moving very, very quickly. But relative to us standing here, it's perfectly still. If I stand perfectly still, my velocity relative to the Earth is 0. So most of the time when we talk about velocity, we mean relative to the Earth. But let's consider a bus. This bus is going 50 miles an hour east. If I drew a velocity vector, it'd look like this. This bus is very special. It's made out of glass, so we can all look in from, we don't have to be on the bus to see what's going on. If someone at the back of the bus walks to the front of the bus at 3 miles an hour, what am I talking about? Do I mean 3 miles an hour relative to the bus, or do I mean 3 miles an hour relative to the Earth? I obviously mean relative to the bus. If somebody walks from the back of the bus to the front of the bus at 3 miles an hour, they're going 3 miles an hour faster than the bus in a way. That would give us this, 3 miles per hour relative to the bus. What would the observer who can see into that glass bus see if there's somebody standing on the side of the road relative to Earth? Relative to Earth, this person's going to be going this fast, 53 miles per hour relative to the Earth. Now, this person went up and asked the bus driver for a date because she thought he was very cute. He said, oh, by the way, I'm very married. Whoops, very married. And she was terribly embarrassed. So she ran all the way to the back of the bus where her seat was. This time she moved back with, say, she was going 6 miles per hour to the back of the bus. Well, if the bus is still going 50 miles an hour relative to the Earth, and she turns around and runs back this way at 6 miles per hour, now when there's an observer watching her, she's only going about 44 miles an hour relative to the Earth. So, relative to the bus, she went 3 miles an hour, and then on her way back, rather embarrassing, negative 6 miles an hour relative to the bus. That's as if you treat the bus as if it's standing still. Relative to the Earth, she was going 53 miles per hour, and then 44 miles per hour. You can think of another similar problem if you think of cars approaching each other. Suppose you have car A, and it's going 50 miles an hour, and you have car B going directly towards it at 70 miles per hour. Both of those are speeds that are measured relative to the Earth. But we can also talk about speeds relative to each other. If you are in car A, you are stationary with car A. You feel like this car is approaching you at 120 miles an hour because that's how quickly that gap between the two cars is going. You would consider car B to have a speed of 120 miles per hour, negative, because it's going in the negative direction. You think of this as being negative. Car B is traveling negative 120 miles per hour relative to car A. In other words, anytime you have a speed, it's relative to something, usually the earth. But if car A says, no, I'm stationary, I'm my frame of reference, then this car is actually coming at me at 120 miles per hour. If you're in car B, you feel like car A is coming at you with 120. So car A is traveling positive 120 miles per hour relative to car B. Okay. There'll be more on relative velocity, I suspect, as we move later. Interestingly, as long as we stick to normal speeds, all of this works. If we have things that start traveling very, very close to the speed of light, all of this actually falls apart and we now need special relativity. But that is a topic for a course another year.